So today, usually Professor Nakamura, Shu Nakamura, the chairman of this colloquium, but he is in Russia. He asked me to introduce Professor Varadhan. Professor Varadhan is well-known, not only programmist, but also as a mathematician. He got Abel Prize in 2007. Also, he gave a special lecture, related special lecture at ASEAN 2010 in India. So then he recently got National Medal of Science from President Obama. This is considered the highest honor in the United States. And also he is a member of the several academies, which I cannot tell it. So many podcasts. So anyway, we are very happy to have Professor Varadhan today. The title of his talk is the right deviations for random matrices and
Thank you very much, Professor Funaki. I'm happy to revisit Tokyo University. The last time I visited was in 1980. I think many of you probably were not born then. So I wanted to talk today about large deviations for random matrices and random graphs. It's joint work with my colleague Saurav Chatterjee. And large deviation theory deals with small probabilities, and you can ask, why does one worry about small probabilities? But if you have a large system, then there are nooks and corners of the system what you want to look at under a microscope, and they have very large probabilities. So you want to ask questions like, what happens if I go there? That means you are looking at conditional probabilities, where the conditioning event is very small, has very small probability. And so you need to understand really how various events with small probabilities relate to each other and so on. So if you have a sort of a general theory that deals with such things, then you can apply it to specific examples, and that's what we will do today. So the object we are going to be considering today are random graphs. So these are large graphs where the number of vertices is very large. So there are n vertices, n is a large number, and each edge is could be either on or off. So let's take a number p between 0 and 1, and we say that an edge is on with probability p and is off with probability 1 minus p. And we are keeping p fixed and letting n become large. There are many other variations of this problem. For example, Yerdash and Rini had a nice theory where p went to 0 with n, but we are keeping p fixed in our model. So that means as this graph gets larger and larger, it's very messy graph. There are lots of bonds from everywhere going. So, but what are the kind of questions we are asking? You can count, for example. Of course, I should have said the different edges are independently chosen. There is no correlation between edges. So you can count the expected number of edges. I mean, there are n choose 2 possible edges, and n choose 2 p. I don't know why I put p square, but anyway, so the expected number of triangles, for example, is n choose 2 p cubed, because then triangle you need all 3 edges to be on. So you can ask yourself the following question: there is a law of large numbers here, that if you actually count the number of ratio of the number of triangles to n choose 3, you expect it to be p cubed, and the very high probability it will be p cubed. And you want to compute the probability that it is different from p cubed. What is it? What is the probability? somehow I got my p and p square mixed up. Okay. Anyway, let us proceed further. So, how many graphs will you have whose triangles are some c times n choose 3? And then if you look at that, how many edges will such a graph have? I mean, you can, the number of edges could be c to the 1 over 3. Somehow I made the mistake all the time. So, see if you, one way you can expect large number of triangles than usual is if you had large number of edges. So, the question you want to ask is it really true that the extra number of triangles you have, the origin is the extra edges? What other alternative is there? Well, for example, it is possible that you have the same number of edges, but all the edges are concentrated in one part of the graph. Then there will be a click there and that will produce more than normal. So, correlations could produce more triangles with a given number of edges. So, you want to know can you determine what happens in any given situation and how do you do that? Okay. So that is the motivation for studying these things. A random graph can be thought of as a random matrix. So, each entry in the graph is 0 or 1, and each entry in the matrix is 0 or 1, and the diagonal entries are 0. It is a symmetric matrix and that represents a random graph. So, you can think of it as a random symmetric matrix Xij of zeros and ones, and this random matrix will have eigenvalues. Now, if you count the number of triangles, it is really trace of the third power of the matrix. So, it is really sum of cubes of the eigenvalues. So, I want to think of Pn as a probability distribution. Well, let me step back a little bit and ask what are the kinds of things I am interested in large deviations. What is large deviations all about? So, I have a sequence of probability distributions on some space, and I want to have a law of large number kind of a thing which says that these probability distributions are concentrating around a point. Then I want to decide how do these probability decay away from that point, and at what rate do they decay? Probably they decay at an exponential rate. That is what one would expect. And I want to determine the constant as a function of A. And in general, this constant may not exist for every set, and so one would expect from general theory like in weak convergence, for closed sets one would expect an inequality to go one way in terms of some function, and for open sets you would have the reverse inequality in terms of the infimum of a set function. And then you can ask yourself, why is it the infimum of a function? It is simply because when you compute the probability of a union of two sets, it is bounded on one side by the sum of the two things and bounded on the other side by the maximum of the two probabilities. So, when you take the exponential rate, you are looking at the log and then dividing by 1 over n, the difference between 1 and 2 disappears. So, basically the rate for the union of two sets will be the maximum of the two, and because of the exponential of minus sign, the constant will be the minimum of the two constant. So, for two sets A and B, the constant for A union B will be minimum of the two constants C of A and C of B. So, one would expect there is some kind of a function, local function I of x, which tells you how the probability decays locally at a point. And then if you have a nice set, or the infimum over A is the same as the infimum over A complement, or A interior is the same as the infimum over A closure, then for those sets you have actually the log will behave asymptotically like a constant. It is just sandwiched between these two. Okay. Then another important thing that one needs to look at, one uses often, is that if you have two different spaces x and y, and you have a large deviation rate property valid on x with some rate function I of x, and you look at the image, the induced distribution on the image space y, and these measures q n will have their own large deviation rate function, and the rate for them is some function j of y. J of y can be computed from I of x by simply taking the infimum over the fiber corresponding to y. It is like saying whenever you are computing probability distribution of functions, there are extra variables, you integrate out the extra variables. In large deviation theory, you minimize over extra variables. So integration gets replaced by minimization. And this function I itself is a local function. It's as its minimum, which is 0 at the point where the delta function eventually is going to sit, because around that point there is no decay of probability, and the function is usually lower semi-continuous, and it has compact level sets, and that just says that if you go very far away in space, if the space is not compact and you go towards infinity, the probability decays faster and faster. So that is important, because at some point you would like to know that there is no contribution coming in from infinity. So, and that is to make sure of that. And the topology is also important, because when you come from one space to another, the mapping should be continuous, and you are talking about closed sets and open sets. So the space in which you prove large deviation has an underlying topology, and this topology is important. The stronger the topology, the better your theorem, because it applies to more situations. Now, usually in large deviation theory, what one does is one gets local estimates. What do we mean by local estimate? We will look at a small ball around some point x and try to determine how the probability decays for this ball. So, you take a very tiny ball around the point x. Well, it may not actually have a decay. So, anyway, take the log, divide by 1 over n. Maybe it has a lim sup and a lim min. I missed the minus sign, should be minus I of x. So, there should be, take the lim sup and lim min, they may be different, but suppose if we shrink the neighborhood as delta goes to 0, in the end you get a common value, which is minus I of x. Then I would say I represents the local rate at that point. Then for open sets, it is very easy to use this local rate and claim that it is in fact the global rate for an open set, because you only want a lower bound for open sets, and an open set given any point there is a small neighborhood contained in the open set. The probabilities are monotone. So, if you have probability for a small ball inside the open set, that serves as a lower bound for the entire open set, and since we are allowed to have arbitrarily small balls, it is true for any open set. So, if you have a local estimate, it is very easy to get a global estimate for open sets. On the other hand, if you want an upper bound and you have it for tiny balls, then you can cover a compact set by open covering, and you take a finite subcover. Finite number does not make much of a difference, because the exponential rate of a finite sum is no different than the maximum of the rates for each one. So, if you have a compact set that can be covered by a finite number of these balls, then you have an upper bound for them. So local estimates give you lower bounds for arbitrary open sets and upper bound for compact sets. So, if you want to go on for an upper bound for arbitrary closed sets, then X is not compact, then you have to make sure that what is outside of a compact set is irrelevant, and that requires what is called a tightness estimate, which says that given any large, any L which can be very large, you should find a compact set such that if you take any closed set away from the compact set, the probability of that decays faster than e to the minus L times n. So, it tells you outside of a compact set, the rate can be made arbitrarily large. So, any rate comes only from compact sets, okay? And that is how you extend the result from closed sets to from compact sets to closed sets. So, given any L, you want a compact set such that for any C disjoint from K L, you have this estimate. There is one example which is sort of the simplest example one can have. You take a sequence of independent random variables with a common distribution, and then you look at the sum, the arithmetic mean of these n random variables. The law of large number says that S n converges in probability to the expected value of x I, and then you can ask what about the large deviation rate function here. There is a large deviation for S n, the normalized average, and the rate function is given by this formula. Now, if you notice, this formula is the Legendre transform of log of the integral e to the theta x d mu. So, by Jensen's inequality, log of e to the theta x d mu is a convex function of theta, and what you have here is the Legendre transform of that convex function, which is another convex function h of x. And you can sort of generalize. Oh, it does not look nice. I did not take it right. Okay. So, you look at, no, this is the wrong version. So, okay. I corrected it, but somehow I think I gave the uncorrected version. Okay. So, what it is, it should be x I j. So, let me draw a picture just to, because So, what I have here is a square. I have points I j and I have x I j, and for any region I am looking at 1 over n square times summation of these things, and the spacing here is 1 over n. So, that the square has n square points. So, I am looking at some sort of an average over volume or areas. So, now you can think of Ln as a measure on the space of on the square, because it is a bunch of delta functions suitably normalized. So, for the whole square is going to have measure 1, because there are n square sides and so on. So no, sorry, x i's are not random variables, they can be positive or negative. It is a signed measure, in fact. Okay. So, M is the space of signed measures, and I want to have a large deviation principle for these measures. Okay. And the rate function here, what is going to be the law of large numbers here? The law of large numbers will be, if the mean of x's is some number a, which may be 0, then the limit is going to be a times Lebesgue measure. That is what the law of large numbers would say, because when you divide by 1 over n square, normalize, the law of large numbers will say that it converges to a times the Lebesgue measure of a. So, the large deviation rate function is going to be some rate function defined on signed measures beta, and the answer is the sign measure beta should be absolutely continuous with respect to Lebesgue measure, otherwise the rate is infinite. The rate does not have to be finite, because around certain points you could have decay which is faster than exponential. So the rate function is finite only if you have a beta which is absolutely continuous with respect to Lebesgue measure, and if f is the Radon-Nikodym derivative, then the rate function is given by h of f x y dx dy. H is the old function that we saw earlier in connection with the large deviation for sums of random variables. As I said before, this is a joint work with Saurabh Chatterjee. So, we want to use this large deviations for random matrices. Now, if x equals xij is a random n by n matrix, of course, in the graph case it is just 0 or 1, but there is no reason why you have to limit ourselves to 0 and 1. We could consider other entries as well, and then we would be looking at general random matrices rather than just random graphs. So in some sense the theory should apply for both, although our immediate interest is random graphs. So, for the random graphs, I need to assume something about the entries. Of course, if it is 0, 1, it is bounded, but if it is arbitrary random variables, I need to have some control on the size of it. So, I need to assume that expected value v to the theta x square is finite. So, it is better than Gaussian. Gaussian is not sufficient. The tail must be faster than Gaussian. You can assume that bounded, for example, which is good enough. And then you can look at the set of eigenvalues. And if the mean is some number different from 0, then there is one eigenvalue which is asymptotic to n times a. That's one can almost see it, because if you just take the row sums, the row sums are all nearly equal to n a by the law of large numbers. So, it suggests that there is some kind of an eigenfunction approximately which is a constant, and the eigenvalue corresponding to that is n times a. So, there is one eigenvalue like that, and then the Wigner's theorem applies for the rest, and so you have all the other eigenvalues are like square root of n, and when you suitably normalized, you have Wigner's semicircle law, which has this form. So, what happens when you normalize by n? When you normalize by n, you have only one value surviving. All the rest of them have to go to 0. The kind of large deviation I am asking is it possible that when you normalize by n, you do not go to just one point A, but you have some other spectrum. Maybe A has gone away, maybe something else has come in, maybe what can we say about in general about the S. So, the rate function we want to compute as a function of the spectrum, and if the spectrum consists of just a single point A, the rate function should be 0, and for all the other things the rate function should be positive. So, the question is, how do you do that? So, the way we are going to do that is, you want a space. If you want to do large deviations, first of all, you can't have spaces that vary with n. You should have one fixed space to work with. So, the space we are going to work with is, we are going to embed all these matrices into the unit square as a kernel. Okay. So, the kernel is going to be defined on the unit square. It will be a symmetric kernel, and the embedding is done like this. Jin is the indicator function. You take the interval, you divide it into, even better, you take the square, divide it into n square uniform subsquares of size 1 over n, and put the entry xij as a constant in each subsquare. That gives you a kernel K, and that is what is one way of seeing it. If that is your matrix, that is your kernel. Just put boxes around it, that is all. So, that you can think of it as a random kernel, and I want to know what is the large deviation for this. Now, it's just the law of large numbers will tell you that in the end this will converge to constant A, which is a kernel whose eigenvalue is just A, and then all the rest of the eigenvalues are 0. So, in some sense what you are interested really is the large deviation theory for K, and you want to compute then infer from it something about large deviation of the eigenvalues. So, if I can do large deviations for K, then I can do large deviations for the eigenvalues, just read off from it, because K to its eigenvalue is just a function. Okay. So, I can project from the kernel to its eigenvalues, I hope. So, what kind of a K are you considering? Well, since I have a bounded function, I can look at Hilbert-Schmidt kernels, square integral kernels, and actually the ones I have are bounded. So, K n is the range of all the n by n matrices there, and I have the Cramér rate function, and just as the example that I wrote there tells you, my rate function is this. So, I have in fact a large deviation principle for matrices for kernels with this rate function. So, why can't I just project and get the answer for eigenvalues? Well, topology is the problem, because this LDP for Qn on K, the rate function is I is fine, but the topology is the weak topology. And in the weak topology, the mapping from a kernel to a spectrum is not continuous. So, I can't do it. So, if you can prove the large deviation principle in some topology where K to Sk is continuous, then you could do the infimum over the fiber and get the large deviation principle downstairs. So, can you think of a topology in which K to Sk is continuous? Strong topology is okay. If you can prove the large deviation principle in the strong topology, then for kernels, they are all bounded kernels. So, it is actually in the Hilbert-Schmidt norm, and if it is in the Hilbert-Schmidt norm, the spectrum behaves very nicely. So, there is no problem. But there is no chance of proving anything in the strong topology, because even law of large numbers is not valid in the strong topology, because the x's are order 1 objects. So, there is a lot of fluctuation here. These are highly oscillatory things, oscillating as you please in tiny squares. So, unless you average, it is not going to converge, and averaging means you are interested in the weak topology, not the strong topology. So, you cannot have a theorem in strong topology, and weak topology is no good. So, what do? You hope there is a topology in between the two, slightly stronger than the weak topology and slightly weaker than the strong topology. There is in fact such a topology, and it is called the cut topology. Now, I had not heard of the cut topology until I started looking at this problem. I don't know how many of you know what the cut topology is. It is a very unusual topology. It was invented by graph theorists to study graphs. Maybe I will say a little bit about the history of the topology. So, we will use it in a way again when we come to graphs. So, the idea is you have graphs larger and larger graphs with lots and lots of edges. The number of edges is the order n square. So, it is very dense graph, and the graph is the number of vertices is going to infinity. And you want to know, I want to take a limit of these graphs. I want an object which I say that this object is the limit of these graphs as n goes to infinity. What kind of an object can it be? Well, you ask you, what I want then is I want to know what am I really interested in this graph. Well, I would like to know how many edges are there. Roughly, I expect the, if I look at the number of edges and divide it by n choose 2, that will tell you proportion of edges compared to the complete graph. So, I can ask how many triangles I have, how many quadrilaterals I have, how many pentagons I have. So, every finite graph gamma, I can ask how many times does it occur in my graph, and how many times will it occur in a complete graph. I can take this ratio and say my graph has a limit if all these objects have limits. Okay. So, that means now it is a strange thing, my limit of a graph is not a graph, but just a function from the space of finite graphs to real numbers, numbers between 0 and 1. Okay. Now, you can ask yourself, what kind of functions do I get this way? The theorem is the set of functions you get this way are precisely symmetric functions on the unit square. Okay. And the way you compute, for example, if you want to compute the triangle here, the triangle is computed simply by integrating f x y times f y z times f z x dx dy dz. So, it is like your third power of this kernel trace is what you see the number of triangles. So, for any graph gamma, there is an object like that you can compute from this function. Or another interpretation of it, you think of the vertices being located in the unit interval equally spaced. And if you want to connect an edge I to a vertex I to a vertex j, that link exists with probability f of I over n, j over n. So, there is a random graph. So, it tells you in some sense any graph is like a random graph, and f is the probability of an edge being there between x and y. There is some that kind of an interpretation. Okay. So, what kind of a topology should one want here? The topology one wants here is the smallest topology with respect to which all these functions are continuous. Because I have a bunch of functions from finite graphs. So, I have it here somewhere, but maybe I will write it now before. So, the object is you look at f of x I x j, product over all the edges, integration over all the x's. That is a function psi for each gamma. Okay. And your topology on the f's is such that all these functions are continuous for every gamma. That is what you want, because that is the way I define graph limits. So, if I want to be consistent, this should be the topology, and that is what topology is. That is a messy topology to do, but it is equivalent to the following. In the usual weak topology, in the usual L1 topology, which is a strong topology, you take two kernels and you multiply it by a function of two variables, integrate with the test function, and take the supremum over all functions bounded by 1. In the cut topology, you limit yourself to functions which are product functions. So, you look at this k 1 minus k 2, take the supremum of the integral with respect to phi x times psi y, where phi and psi are bounded by 1. That defines the distance between k 1 and k 2. Or it is equivalent to integrating over product rectangles A cross B, where A and B are Borel sets. If A and B are intervals, that is essentially weak topology. If you take the supremum over all possible Borel sets in the plane, that is strong topology. And the cut topology is something in between, and you take just the supremum over all possible rectangles A times B, where A and B are Borel. Okay. Now, it is easy to see that if the distance, if the distance between k n and k goes to 0, then all these integrals that I wrote down, they are all continuous. You can do it just by integration one step at a time. So, in particular, the spectrum converges simply by looking at all cycles, all graphs, pentagons, hexagons. If you take all of them, that compute all the powers of eigenvalues. You have got to start bigger than 3, you can't do it for 2. 2 does not work, you have to look at 3. The reason is because the 2 is bad, you go and come back, it is not linear. If you go 3, then you do not do the same edge twice. Okay. So, as I said, you count the number, I think I said all of this, divide by the ratio exists for every gamma, what are all possible limits, and you want a representation of it. There is a symmetric function f x y and 0 cross 1, and that is the representation I had on the board. And the cut topology is one for which all these are same. So, next thing you want to do in the representation is the function f unique that represents a curve gamma, that represents a graph. Well, it can't be unique, because if you have two functions related through a measure preserving transformation of the unit interval, all the integrals are the same. That is to be expected, because when you compute the number of triangles, number of subgraphs and so on, how you label the vertices of the graph is irrelevant. So, there is a permutation group on the vertices of the graph which leaves the problem invariant, and its trace when you pass to the limit will be the measure preserving transformations of the unit interval. That is a group that leaves the problem invariant. So, you have to say that f and g more or less have the same thing in this object if one is transformed or the other through a measure preserving transformation. And the cut topology is the smallest topology that makes it continuous for every gamma. Now, in the cut topology, the law of large numbers is valid. The reason for that is, although there is a supremum involved, you have to ask yourself, how many objects do I have over which I have to take the supremum? It is true, I have all possible Borel sets A cross B, okay, but A does not have to be any Borel set. Basically, the problem is based on intervals, n intervals. So, all the sets I need to do are all possible finite combination, finite unions of intervals. There are n intervals, each one can be in or out. So, there are 2 to the n possible choices for A effectively, and there are 2 to the n possible choices for B effectively. So, altogether there are 2 to the 2n choices. But my random variables are n square in number. So, the large deviation rate function for that is going to be not like e to the minus n, but e to the minus n square, and e to the minus n square is a lot smaller than you know, even if you multiply it by 2 to the 2n, it still goes to 0. So, it does not matter. So, the law of large numbers is valid in the cut topology. It is not valid in the strong topology. In the strong topology, you need to have all possible combinations of sets, and such sets are n square in number. So, now you have to worry about 2 to the n square, and you can't do that. Okay. So, that is why law of large numbers is valid in the cut topology, but not in the strong topology. Okay. Now, you want to prove large deviations in this cut topology. Lower bound is fairly straightforward. It is done by what is known as tilting method. You have something called Cramer's tilt, which is you replace the random variable by the distribution by a new distribution with an exponential tilting, and you adjust the exponential tilt so that the mean is what you want. So, if you want, and then the relative entropy for that you can compute, and that is what Cramer's rate function is. And if you want the mean to be some f I j, then you have to tilt it accordingly, and then the law of large numbers is still valid, and you compute the relative entropy, and it gives you the lower bound. And it is a standard method of tilting that one can use. The upper bound is where the trouble usually is here. The upper bound involves taking unions of small balls, so you need some compactness to do the upper bound. Now, compactness is not there even in the cut topology. The reason compactness is not there is because although cut topology is weaker than strong topology, if a sequence converges in cut topology, if you integrate one variable, then the integrated function of one variable converges strongly in the cut topology. That is because you have supremum over all possible a cross b, and if you take b to be whole space, which is what integral over that corresponds to, then you are left with supremum over all a. Supremum over all a is strong topology. So, these functions of two variables that converge in cut topology, once you integrate one variable, the function that comes out converges in the strong topology. And you can't have compactness in the strong topology, it is not there. So, what do you do? Then you ask yourself, what am I missing here? What you are missing here is the problem is invariant under a huge group, n factorial there, and the effect of that is the measure-preserving transformations of the unit interval. So, what I should really be doing large deviations not on k, but on k mod g. G is a huge group, k is not compact, but maybe k mod g is compact. And it does not matter for my purposes, my problem is invariant under G, I can prove my large deviation theorem on k mod G, and that would be just fine for my purpose. Fortunately, there is a theorem due to Lavage and Szegedy which says that k mod G is compact, and it is based on Shemered's regularity lemma, and it is a technical lemma. What it really says is it is a discrete version of Lavage and Szegedy's theorem, which says that somehow any graph you can think of is very close to one of these random graphs, okay, and it is uniformly so irrespective of whatever graph you choose, and that is regularity result. So, if you use that, that is originally proved for 0 1 matrices, okay, because it was done in the context of graphs. Now, it was later generalized to graphs which are not 0 or 1, but have finite set of values, multicolored graphs. Now, if you have a bounded random variable, you can chop it up into finite grid and basically approximate it, and it all goes through. So, that is not a problem. So, since K mod G is compact, it is enough to prove local bound. Okay. The local bound you can easily prove in the weak topology, okay, because large deviation theorem one could easily prove in the weak topology. But small balls are weakly closed anyway. So, so even if in the strong topology, the problem is not for proving small balls, it is then for covering is the problem. So, what you want to do then? You want to take the small ball and take its union over the orbit, and you want to prove an upper bound for the orbit. There will be a small ball in the quotient space, and then quotient space is compact and you are done. So, the only question is how do you go from a small ball to the entire orbit? The orbit is very big, the group is very big. Chamarette regularity lemma says you do not have to worry about the entire orbit, you just look at the permutation group that acts there. Permutation group is just n factorial things, and n factorial is only e to the n log n, and n log n is still smaller than n square. Okay. So, it works fine in the quotient space, and that is how you prove large deviations in this space, and that establishes what you want to do. Now, then if you want to extend it for unbounded things, you use little truncation and then you prove the large deviation for the truncated one. Now, why do we need the condition that it should be faster than Gaussian? What happens if it is Gaussian? Well, if it is Gaussian, you are looking at large deviations with rate e to the minus n square. A Gaussian random variable can be as big as n, and the probability would be e to the minus n square more or less. And just one value of n in a matrix could give you an eigenvalue which is like n. So, if the tail is just like Gaussian, single entries become influential, and you want to avoid it. You want to make sure that anything that matters is somehow smoothed out, and that is why you can't get rid of this condition. If you do not have it for the Gaussian case, I have not done it, but if you do it, the answer will be somewhat different. Then you remove cutoff, and then you do some standard things that you do in large deviation theory. Okay, let us go back now to random graph. So, in the random graph, what you are interested in is, okay, how do you compute the rate function for these things? And you can also compute for quadrilaterals or any kind of graphs you want. And what are the questions you want to ask? The probability for, you can ask questions like what is the probability that you have so many triangles, so many quadrilaterals, combinations thereof. These are all now things that you can handle. Another thing you want to ask is, if the number of triangles is more, what kind of a graphs contributed to these things? So, these are all done now by doing large deviation and K mod G, and you have an explicit rate function, which is a Cramér rate function for the binomial 0, 1. You can write it down. It is just k log k over p plus 1 minus k log 1 minus k over 1 minus p is a very explicit function H p. And the rate function for the triangle count, you just have to do a variation problem, because it is just a minimization that you need to do. You want the number of the ratio of triangles to be C, you want a kernel whose triple integral is C. And then the infimum you want to minimize the rate function 1/2 integral h p k x y dx dy. The 1/2 comes because I have symmetric matrices, and so I need only half the triangle and not the full square. So, I have a variational problem of fixing C and minimizing the entropy. That is what calculus of variation wants me to do. This is the fiber, and I want to minimize over the fiber. So, the infimum, I can do an Euler equation and get the infimum, hopefully, and that is what the Euler equation is for the infimum is attained. Now, if my C is very close to p cubed, that means I want only slightly more or slightly fewer triangles than what is expected. That forces beta, beta is the Lagrange multiplier here, that forces beta to be very small. It is just analysis that you have to do. And then you can write down an equation which has only one root. Anyway, the upshot of the analysis is that in that situation, the Euler equation is only constant solution. That means the infimum is attained at a constant. That means the best way to achieve slightly more or slightly fewer triangles is to adjust correctly the number of edges either up or down. Right? That is what constant solutions mean. That means the whatever you do is uniform over everywhere, and you just adjust the rate probability of an edge. It either goes up or down. Remember, f, the interpretation for f is the probability of an edge. So, f is a constant, slightly different from p. Okay. So, what it proves is really a theorem. The theorem says that if you count the number of graphs with number of triangles very close to some number c, which is close to p, then the number of edges would be like this. Then the number of quadrilaterals, all the other things would be like a graph with probability c to the 1/3 or whatever. Okay. But that is not true if you go far away, because if p is very small and you want a lot of edges, then what you need, you do not have to spend your resources creating lots of edges. If you carefully create edges in a corner, you can get your number of triangles with lot fewer edges, and you have to pay for each edge. The entropy cost is enormous if p is very small, and if you want an edge, remember it is log of 1 over p. So, it is huge cost, entropy cost of creating an edge, and you do not want to create more edges than you have to. So, the optimum is nearly, that means cliques form, and the cliques are responsible for the extra number of triangles. Similarly, on the other side, if you want fewer triangles, again if you have lots of triangles and you want very few triangles, lowering p to a low level is again expensive, and you do not want to lower more than you need, and you need a bipartite graph has very few triangles. So, you selectively cut certain number of edges, and then you achieve your end, and the entropy cost is much less. This tells you there is, in fact, when you look at this conditional distribution, there is a kind of a phase transition with one type showing up when c is near p, another type showing up when c is far away from p. So, I think that is about what I wanted to say, and the important thing here is that large deviation is used as a tool to answer some questions on combinatorial issues and so on. And especially when you want to calculate conditional probabilities, where you have to divide by an event with very small probability, converting it to a variational question, then the properties of the variational solution tell you what happened and what caused the large deviation. That is the idea of the thing. Thank you.